Okay, in 2004, the WSC started what I think is a really wonderful tradition of the Titans simulation talks during lunchtime. And it's an honor to continue that tradition here in 2013. Today's Titan speaker is Richard Nance, Emeritus Professor of Computer Science at Virginia Tech, received his BSIE and MS degrees from North Carolina State University in 1962 and 1966, respectively, and his PhD from Purdue University in 1968. He served on the faculties of Southern Methodist University and Virginia Tech, where he was the department head for computer science from 1973 to 1979. Dick is the author of over 150 papers on discrete event simulation, performance modeling and evaluation, computer networks, and software engineering. He's held several editorial positions and was the founding editor-in-chief of the TOMACS, ACM Transactions on Modeling Computer Simulation. He served as program chair for the 1990 Simulation Conference and was instrumental in the development of the Simulation Archive at North Carolina State, which, if you haven't picked one up, you should get one of the bookmarks for the Simulation Archive. He's received several awards for his editorial and professional contributions, most recently the Lifetime Professional Achievement Award from ISIM, the Informed Simulation Society, and he was elected a fellow of both the Association for Computing Machinery in 1996 and the Informs in 2008. In 2006, he was recognized by the faculty of the Edward P. Fitz Department of Industrial and Systems Engineering of North Carolina State as one of the 12 distinguished alumni over the first 75 years of department history. It's my distinct pleasure to turn the stage over to today's Titan speaker, Dick Nance from Virginia Tech.
Thank you, Ray, and let me begin by thanking you and Mike Cool and anyone else who had a part in giving me the invitation to speak here. It is indeed an honor, and it is one that I hold dear, being at least an associate conniver in the restart of this conference in 1976. I plead guilty. 50 years, simulation and software. I'm a dinosaur, you know? But as I'll get friends to attest, I'm not a T-Rex. I think I'm probably more like a brontosaurus. Do you remember the brontosaurus, the big, huge body with the small head on one end and the reputed divided brain between the head and the posterior region? Some women have said men have been that way all the time. But having seen a lot, I will share with you the experiences in this, I think I will, in this presentation, which extends over the following subtopics that I'll just let you read. I'm going to try to keep it light. I will welcome polite questions, even polite disagreements. Please, though, no throwing of things. Okay? The objective with this Titan presentation is neither broad nor comprehensive. What I'm trying to do is give you one person's experience, which I think is probably very indicative of people who came along about the same time as I and were fortunate enough to work in areas related to computing, computer software, and modeling and simulation. So the focus is going to be on those influencing factors for someone through 50 years of working in a technical area that itself was emerging and self-defining during that period. I'm going to talk about persons, personal interactions, and obviously there's going to be an influence from organizations that I associated with and organizations that I worked in. Technology advances. Boy, it's hard to look back in 50 years and identify an area that's had more influence from technology advances. I was writing part of a section in a book in 1968, and I speculated at that time on 100 years from now, will this be known as the atomic age, or will this be known as the computing age? In 1968, I probably wouldn't have had many takers on the computing age, but today I'm not so sure. I'm also going to talk about educational shifts and how they've influenced the career, in my case and in many of yours. And then the one surprising factor, at least it was for me in thinking about it, but perhaps not as unusual, is a classical problem. In my case, the machine interference problem. It kept coming back, I'm not sure, to haunt me, to inspire me, or to humiliate me. Maybe all three on different occasions. Very quickly, a pre-graduate education summary. As Ray said, I got my bachelor's degree from NC State in 1962. I went to work for the Procter & Gamble company in Cincinnati, and about 16 or 18 months into my stint there in Cincinnati, I decided I really wanted to go back to graduate school. I really wanted to work in operations research with a knowledge base that allowed me to do something. I was part of an operations research minor as a baccalaureate degree, but I really didn't know enough to pursue the kind of career that I envisioned for myself, at least. So, even while I was at Procter & Gamble, I began to prepare myself, and I got myself one of the basic tools. In fact, probably the most important tool, and some of you will recognize it. That says IBM Charting and Diagramming Template. And that's how we approached computer problems in that period. We drew a flow diagram or a flow chart. And this was very important. You might be able to tell that it was well used. I don't think my laser's going to carry quite that far, and I don't think it'll help if I point it here. One in particular, the circles on this, or oblongs on this, is ink stain, meaning that I used it so often that the ink was getting onto the template itself. I'm going to now give you some introductions. My introduction to discrete event simulation. I had some introduction to Monte Carlo simulation as an undergraduate, doing it by hand, using that famous table out of the back of a statistics book. But with my MS thesis problem, suggested to me by Professor Robert W. Llewellyn in the textile industry, I was going to use discrete event simulation to solve a problem. Now, I heard the term simulation. This is after I'd just gone back from my master's degree at NC State. I heard that term, and I said, should I ask what it means? Because maybe I'm being, demonstrating ignorance if I don't know what it means. And then when I decided, well, I can ask this person, I usually got the response that indicated that person had no more clue than I as to what discrete event simulation was all about. But when Llewellyn introduced it as looking at a problem in the textile industry, he described how we hopefully would produce a solution to this problem. The problem was the machine interference problem. It's a classical problem. The major source that I worked from was a paper in the Journal of Industrial Engineering in 1958, which was actually a translation of a paper from 1947 in a Swedish journal. Docent Conny Palm, probably mispronounced the first name, was well known in the Swedish applied probability statistic domain. And he had published the paper that had drawn so much attention that industrial engineering had decided to print a translation of the paper in English. The solution was obtained via a recursive formulation in finite queues. And probably those of us who have gone through at least the beginnings of queuing theory can remember how that kind of thing worked out. You made your formulation of getting from one state to the next, and then followed that to the last state, and then did a backwards recursive solution. Llewellyn had done some early work and had supervised 2 students working in the area. But in my case, the issue was what was called ancillary work. In the textile industry, the idea was to get the operator to do various job-needed tasks while remaining attentive to machines. And the machines that we were talking about were semi-automatic in nature, and they operated but could fail randomly. And the issue was how many machines to assign to a single operator to get the balance or minimize the total downtime cost for machines and operator idle time cost for paying, for no work being done. So this was the textile system problem that I was addressing in my master's research. Now, the machine interference problem is deceptively complex. By particular repair strategies, you can lead to a rather simplification of the solution approach. You can repair machines in the order of their failure. You can repair machines according to which is the nearest to you as an operator when a failure is encountered. Or the third approach, which I was using in my thesis research, was the patrolling machine repairman, or the machine operator goes into mode as the beginning of a tour, and that tour is unidirectional around the perimeter of the machines, and this allows for ancillary work, filling oil reservoirs, other things, maybe placing some bobbins into the proper location for replacement. And how many machines, though, can we assign? And the assumptions about the problem solution greatly simplify or make a solution more amenable, such as the travel time is negligible. Well, travel time is negligible means that you can really kind of twist the problem around and say, if these machines move, they'll form. If I do it right, they'll just form a queue. And if I assume that I have a large number of machines, I can actually get an approximate model through an MM1 queuing model. Pretty simple, easy to solve. That also, has the assumptions that the exponential time between failures and that there's an exponential repair time. Now, earlier solutions to the problem had not followed all of these assumptions, but had tended to follow the travel time as negligible, which made it certainly amenable to solution. But with the patrolling repair, that assumption just didn't make sense. So I began to attack the problem. I developed a crude sketch and a flow chart using my handy template. And then I began writing a Fortran program on the IBM 1410. I don't know whether to say, oh, here's a 1410. 1410 was an interesting machine. It was a variable word length machine. That is, you could specify what word length you wanted to use. That I would characterize as good news. The bad news, it was a decimal arithmetic machine. Slow. So I began by generating my subroutine for applying the ancillary work strategies, you know, to lump them all up in one tour, spread them out over multiple tours. And then I went on to produce a program that would use and interact with this subroutine. You notice I have to mention verification because Bob Sargent's in the audience and Osmond Balgy's in the audience, and you just don't talk about doing simulation without recognizing verification and validation. I did very little verification. We didn't know about it at the time. We didn't know that should be a good process for developing a program that would lead to, hopefully, a successful result. I did do some validation. We had a solution that Llewellyn had supervised in an earlier thesis on an IBM 1620. Another, okay. I did the recursive formulation there and compared the results, of course, excluding ancillary work as a part of the problem. And lo and behold, the results differed. They did not compare well. They failed the t-test of comparison. So here is a very crude, very abbreviated characterization of the conversation I had with Professor Llewellyn. He asks, how is the next repair computed? My answer, I'm doing a sequential comparison of clocks. Well, what I meant was that each machine had a clock, and the repairman had a clock, and the repairman's walking around, and all I do is compare one clock to the other, and obviously if the machine clock is less than the repairman clock, there's been a failure. So then you have to compute the time to bring the machine up to current time, generate a time to next, generate a repair time, and then generate a time to next failure. Llewellyn, when I gave him the sequential comparison of clocks answer, said, let me examine your program. And I, of course, said, please do so. And after that arrow indicates a delay of a couple of days, Llewellyn was pretty prompt. He said, your code is correct. And I said, well, a key comment had come up during the time that Llewellyn was talking with me about my results. You notice he said, how is the next repair computed? He was indicating, when is the next event of importance occurring? How do you determine that? And my naive response was, I do sequential clock comparison. Just to finish off my study for the master's, the ancillary work strategy had no direct effect, no noticeable effect on system efficiency. That's taking the total time down for all machines, adding it together, and over the total operating time, and subtracting that fraction from 1, and you get the machine or system efficiency. And that was my first journal publication in Textile Industries, February 1968. Now, while I was at NC State, I began to expand my horizons. I learned about gaming. It's so interesting, isn't it, that gaming was almost a couplet with simulation back in the 60s. You didn't mention simulation often without mentioning simulation in gaming. If you're an Informs member, one of your predecessor organizations was called the Timms College on Simulation in Gaming. Okay, if I'm adding a little bit to your storehouse of worthless knowledge, I'll take credit. I had a friend who was working in the master's program named John Soden, and John wrote a game North Carolina State University Game 1, and in discussing his approach and his techniques, the idea of this game was to make students in production scheduling better understand what their challenge was. And so they would schedule machines or the production cycle for machines according to the game rules and input those through punch cards that John would take to the computing center and submit, and we would get, well, they would get a result. Interestingly, of course, one of the most important things in gaming today is the interface between the game and the game player. And that wasn't much of an issue in 1968, 65, 66. I also was introduced to industrial, nay, system dynamics. It was called industrial dynamics in 1963 when Llewellyn took the MIT summer course. And from that, he developed the course at NC State. He also developed a simulator called Fortran for industrial dynamics, again running on the IBM 1410, running often long times on the IBM 1410. But you could do industrial dynamics, whereas Dynamo, which was the language used at MIT, was not installable with the limitations of the 1410. Industrial dynamics, for me at the time, was intriguing, and its creator even more so. You know I'm a history bug, so I have to tell you just briefly, its creator was a fellow named J. Wright Forrester. Forrester was a graduate student working on the Whirlwind project in the early 50s. And Forrester discovered and held a patent for magnetic core memory. Also interesting about Professor Forrester is that during the midst of discussing the sale or royalties derived from his patents with IBM lawyers, he fired all his lawyers and went down and discussed them in person. So Forrester was an interesting person, very outspoken, and there was a good bit of controversy from the start about industrial dynamics. I don't think things have changed much. Uh-oh. We got it. I left NC State and went to Purdue to do a doctorate. I wanted to work in operations research, but I had very strong feelings about where I wanted to go. I wanted a strong statistics department. I wanted a computer science graduate program, and there weren't that many in the mid-1960s. Purdue and Stanford argued about which one was older, which one was first. I can tell those of you from North Carolina that Fred Brooks was wrong. They were not first. I was there, and he wasn't. Okay? I wanted some flexibility in the courses comprising the study plan, and the Purdue School of Industrial Engineering gave that to me. And during the first semester, I received a research instructorship to work with a NSF-sponsored research program. And that was great because the program, the project looking at operations research studies in libraries stimulated my interest in automated information storage and retrieval. And it also gave me an avenue to expand my application and learning of industrial dynamics modeling. The university and school were a major transition because it was so much larger and so much broader than what I had been used to at NC State. The computing resources were like stepping into heaven. An IBM 7094 could execute those programs that took an hour and 20 minutes on the 1410 in about 2 to 3 minutes. I love the 7094. I probably would vote it as my favorite IBM machine of all time. We also had, on the grant, resources that permitted me to actually make a trip to NC State to discuss problems with Professor Llewellyn, because no one was a real authority or was working in system dynamics, industrial dynamics at that time at Purdue. But the the gentleman you see pictured here, from left to right, Ferd Limecooler was the project director, principal investigator, and Ferd was not at all stingy about giving resources. We actually had Ed Roberts from MIT come in and give a seminar on doing industrial dynamic studies of research organizations. The fellow in the middle was my principal, I won't say that. I was going to say principal protagonist, but Norm and I, Norm Baker, some of you might know, he went to Georgia Tech from Purdue, went to Cincinnati, and became senior vice president and provost at Cincinnati after he went there as the head of the Department of Quantitative Analysis, I believe, in business. And the guy on the right is about a 1970 picture of Marcel Newts. Anybody know Marcel Newts? Okay. He and I were struggling at the time to try to do something with formulating a transition matrix for a semi-Markov process. And you would look at the state to which you transitioned and the residence time in that state, and theoretically be able to theoretically be able to extend that through matrix multiplications, actually convolution of distribution functions, to get a solution that would not rely on simulation for a particular queuing problem. We had a problem, though. I was still waiting to learn about distal, dynamic storage allocation language. I didn't know about it. I'm not sure it would have solved the problem, because we still had the problem that the only way we'd get a solution here is to be able to, for the program during execution time, to return memory to the operating system. And we weren't at that point. I discovered an intriguing course in the Krannert School of Industrial Administration, taught by a guy named John Dutton, using a classical textbook, as it was recognized later, Computers in Thought, edited by Feigenbaum and Feldman. And if this was a collection of papers from the most notable names in AI at the time, or topics like machine learning related to artificial intelligence. I found myself over the years going back to this book until once I discovered I couldn't find it on my shelf anymore. No doubt it was a loan to a student who forgot the source of the loan. So many years later, I happened to be serving on the National Academy of Science, a panel that does annual evaluation, not an annual necessarily, but there's an evaluation done of the National Bureau of Standards, now the National Institute of Standards and Technology. And Ed Feigenbaum was serving on that panel with me. He was at the time on leave from Stanford and was chief scientist of the Air Force. And I bemoaned my loss of my book, Computers in Thought, that I had used as a text in the Krannert School Simulation of Decision Making course, is the title. He said to me, they've just decided to reprint that. Oh, I said, would you please let me know how I could get a copy? 2 weeks later, I had a signed copy from Ed. Information storage and retrieval became something of a second area, maybe even progressing toward a first area, a guy named Bob Corfage. at Purdue, who was very quick to point out the capabilities and limitations of digital technology. And the limitations were many at that time. It's hard for me to think that I could have envisioned the search engines of today from that point in the 60s, looking at what we were trying to cope with. I also remember lasting friendships. I haven't seen Steve here today. Is he? There he is. Thank you, Steve. Steve Roberts and I were at Purdue together, continued to communicate. He went to the University of Florida, worked on something called Insight, and we have held a friendship for many years. I leave Purdue to launch an academic career. It was easy to select where I would go. I wanted something that would allow both operations and research, allow both operations research and computer science research to coexist and be rewarded. And so I joined the Computer Sciences Center at Southern Methodist University. And it truly was a place where operations research and computer science existed on a more or less co-equal basis. And the more or less could get troubling, but more or less is a good descriptor. I transitioned my PhD research. Norm Baker and I published a couple of papers. But this problem on machine interference continued to nag at me. Why did Llewellyn ask the question, how do you determine the next repair? Well, that soon was followed by the question in my mind, can I do it? In other words, not just walk the operator around the perimeter of the machines, but can I find where the next repair is going to take place? And if, in the 1968 to 70 period, it was a critical juncture for simulation. We had numerous simulation programming language advances. We were on, some of you would say, GPSS 360. Oh yeah, but we were also on GPSS UNIVAC. And there were control data implementations as well. SimScript 2 had just made the scene, and it was having a major impact in modeling large military or logistics operations. Simulus 67 was yet to make its big splash, but was starting to get noticed. And then GASP 2, the language created by Phil Kvyat, working with United States Steel in the early 60s. Kvyat, of course, had moved to RAND and was working with Harry Markowitz on SimScript 2. We also saw an educational shift. Textbooks appear. My goodness. Back when I first started, my challenge was probably to find a programming manual in my selected simulation language and a few papers maybe to give some underlying broader context. But now we get Naylor, Belinfi, Burdick, and Chu, if any of you remember that one, or Imshoff and Sisson, or Evans, Wallace, and Sutherland, all authors of texts that were quite useful and very helpful in teaching a simulation course. We begin to see the research beyond the simulation programming language level. I consider the reports from RAND from 67 to 69, authored by Phil Kvyat, two of them, one on programming concepts, the other one on, or simulation concepts, simulation modeling concepts, and one on simulation programming languages. And then one with George Fishman on simulation statistical analysis. We also had this little book, The Art of Computer Programming, Volume 2, by a fellow named Donald Knuth. and it presented all that I could care to know and more than I was able to learn about generating random numbers. I think one of the event days in my life was being introduced to Donald Knuth at the Stanford dining room. He was having lunch with George Danzig, and so I was introduced to both of them at the same time. This is about 1970. And the person making the introduction was a guy named George Forsythe, who was the father of computer science at Stanford. By the way, George Forsythe worked a little on random number generation himself, Poisson random number generators. He had a paper, I believe, don't hold me to account for this, but I believe in the same proceedings that Derek Lamer's two early papers were published in 1951, I think, tracks of the Harvard Computer Labs. I got to mention this last event, the NATO Working Conference on Simulation Programming Languages, published, the date's 1968. It's by Hollingsdale, if you ever get a chance to read it. It gives an attendee list. It looks like a list of the eminent computer scientists in the UK. Christopher Strachey, Anthony Hoare, and persons of that type. Well, Donald Knuth was there. In fact, Donald Knuth was talking about the simulation-oriented language. He was a co-author of that, developed in 1963 for Burroughs. He was working as a consultant to Burroughs. That's the same one. Uh-oh. Oh. Thanks. Machine interference problem, the nagging questions. I began to understand that Llewellyn's perception was based on an event scheduling point of view. Next event should be the next event that has any impact on the system, and just walking around doesn't. It's when the repair occurs. And so I went about trying to determine, well, if I were able to model the patrolling repairman in using the event scheduling worldview, would it reduce the execution time? Because that was all the argument for the event scheduling worldview. I went about developing algorithms and proving those algorithms with the help of a colleague on one of them. I did experiments on the UNIVAC 1108 with Fortran 5, as it was known on UNIVAC. It allowed you to go in and generate a clock interrupt. You could read the clock, and then when you went through your series of experiments or your iterations, you could go back in, read the clock, do a subtraction, and you had the time it took to execute that on the machine. Now, I frankly admit that you've got real problems with the amount of overhead that can be in there, but if you do it in a relative sense, that shouldn't be all that in error. That clock read and was not new to me. At Purdue on the IBM 7094, we used to do clock reads when our program started, and a clock read when it ended, and we would just basically add 1 second. They couldn't tell you were doing that, and you were cheating them out of all that machine time. Don't tell anybody I ever told you I did that. I discovered in my results that the execution time with event scheduling required more, greater than on all other cases. So I conjectured that actually there was a continuum of time flow mechanisms based on the relationship between time and state that were allowed in the model assumptions. And this publication occurred in 1971 in Management Science. I was very proud of that one. At SMU, it was a research-intensive environment with teaching commitment, and I had some accomplished and well-motivated colleagues. The guy on the left, Harvey Greenberg, was the founder of, or principal founder of the Informs College on Computing, and that college now sponsors a prize with his name on it. Bill Piscala left SMU actually before I did, went to Northwestern. He later became president of the Operations Research Society of America. He was also editor of Operations Research. And my good friend and colleague, Narayan Bhatt. Narayan and I published papers dealing with, initially we were studying networks because of a proposal we were preparing, but then we got into looking at time-sharing systems and modeling time-sharing systems. So my topics of research were broadened. I was looking at random number generation, particularly for limited machines, because we were starting to see the emergence of personals, or maybe more the mini computers, as we were calling them. I was looking at composite combinational techniques, but I was also very interested in model development concepts and representation and communication. How human beings envisioned and saw a solution to a problem, and how different they could be. I also began to look into information transfer networks in studies with Corfage and Bott, and as I mentioned, the performance models of the operating system and computer networks. Now, interestingly enough, as we got into that, we would see that the operating system for time sharing would work more or less like it would have a job initiator. You would get into a group of jobs that were competing for the CPU, and how did you determine which one received the allocation? Oh my gosh, you might do a patrol. You might just check each one to make sure you give a fair allocation, and you do so in a cyclical patrolling type manner. And I was back to seeing the machine interference problem again. I had several PhD students. I mention them here because each certainly had an influence on me. Bill Claybrook did a dissertation in AI, the automatic factorization of polynomials, and we're talking about big polynomials. Donald Crouch and Carolyn Crouch, husband and wife team, did research in information storage and retrieval. I continued after going to Virginia Tech to work with Claude Lee Overstreet, Jr., and that has created a confusion because, of course, later at Virginia Tech, I worked with C. Michael Overstreet, and it was easy to confuse the two, but because of the last name, but Mike and Claude worked in very different areas. Simulation model specification, documentation, and representation sort of replaced the more amorphous ideas about communication, et cetera, and led to a thinking that it manifested itself in the model development environment concepts. We continued to work on performance evaluation models. We had a couple of papers in Journal of ACM dealing with that. And I began to recognize that looking at the model development environment issue was also going to require looking at the systems engineering issue, and I began to work with the Navy. Now, working with the Navy was a very interesting and very beneficial experience for me. I also had, as department head, responsibilities for instruction and student development, and I'm just going to talk about that with anecdotes. This one anecdote, Sugar Bear, you would rather. Well, that came from a quote of a student, a quote from a student of a statement I made to that student in the first year I was department head. We operated remote job entry access to IBM 370s in the computing center. And when these stations were staffed by students, when they would have a problem and they couldn't get response from the computing center, whom do you think they called? Like at 9:30 on a Friday night. And I got called. I went at a brisk pace into the ground floor of McBride Hall, and a student says, "About time you got here." Jokingly, of course. And I said to him, "You would rather French kiss a rattlesnake than tangle with me." And they later put it on a plaque. Sorry I didn't take a picture of it. They put it on a plaque and gave it to me. Events that occurred during this period of time as department head, Simula was installed. We were the first IBM University installation to have a Simula compiler. The history of, Winter Simulation Conference 1976, the restart, fellows like Bob Sargent, we owe a lot to for that, and Paul Roth. And the History of Programming Languages 1 conference took place in Los Angeles in 1978. Fascinating. Now I'm going to perhaps dispose of a myth. Who wants to volunteer to give me the answer? What does B and F stand for? I hear the answer, Bacchus-Nauer form. Okay? How many would you agree with that? How many of you would say it stands for something else? Dr. Hendrickson, I just made you an honorary. Jim is correct. It's Bacchus normal form. Peter Nauer, in a paper at the History of Programming Languages Conference 1, said he had nothing to do with B and F. It was all due to Bacchus. And so if you've held this, I've had people tell me this for many years, and I do my best to dispose of myths, but it's true, and you can go read the paper. The next, I don't know whether to call her a myth or an event, Grace Murray Hopper. She was a student inspiration. She could teach and inspire undergraduates more than anyone I think I ever contacted or came into contact with. Grace had her rods. Anybody here ever see her present? Okay, Ray did, and Jim did. Remember her rods? In other words, to illustrate the differences in milliseconds, microseconds, nanoseconds, she would take a rod that would be the length set so that the electron generated at the beginning of the rod would end its travel in that duration of time period. And of course, you know, when you're talking about milliseconds, she had a long rod. And you get down to nanoseconds, and it's a very small rod. But it did more to display the contrast than just sitting there talking about 10 to the minus 3, 10 to the minus 6, etc. I give her a website here. The pictures, that's probably Commander Hopper, about 1943, 44 on the left. That's Captain Hopper, 1985, in the middle. And that's Rear Admiral Hopper in about 1992, I would say. I was standing in line with I guess it was Captain Hopper at the time in Dulles, waiting for a flight to the West Coast to a fall joint, a spring joint computer conference. And she says to me, you know, they asked me if I would be a chairperson for this conference. I told them, no, I'll be a chairman, though. Grace Grace was also no shrinking violet. At Virginia Tech, we were just before let me stop for a moment. I had stepped down as department head with a year's notice in 1979. I took a year's leave and spent it at the Naval Surface Warfare Center. I think that was the Naval Surface Weapons Center at the time in Dahlgren, and at the Imperial College in the UK. My stint at Imperial College was funded by an SRC research fellowship. With the Navy, I was dealing with distributed computing, a really hot topic of the time. What does it mean? How do we deal with it? How does it affect naval combat systems? We also were dealing with networks and the issue of software engineering. In 1980, there were very few, if any, curricula that identified software engineering as the title, and there was no government services classification for software engineering. You either were a mathematician or engineer, and engineers paid better. So I also at Imperial College began to look at the model representation approach that had dominated in the UK, the activity cycle diagram. And my sponsor there was a fellow named Stephen Matheson, certainly known to some of my good friends from Brunel. And this led to a time and state relationships investigation that produced papers. And then in terms of events, there were 2 simulation conferences, the first in St. Agata, Italy. Oh, that was a conference that was one of those seeking to solve the real problem in simulation, the lack of standardization. Now that was a holy grail, and there were a lot of Don Quixotes out there. I think I gave the lead-off presentation there, and I think it was entitled Simulation Standards, to Be or Not to Be. And my conclusion was, look, if you're working in continuous simulation, you have your specification language. It's called differential equations. If you're working in discrete event simulation, you don't have one, and I don't see one on the horizon anytime soon. These 2 guys at the bottom were involved in that conference in New York City, that's the last one there. Actually, Bob Sargent, who's on your left, I've known for so long that we both try to escape mentioning the date. But this fellow, Osmond Balgi, was dynamic, dark-haired dynamo in New York City. And he never failed to attack, pleasantly so, those who he thought were misguided. And I was one of those at the time. I was using the wrong terms for validation and verification, but I explained myself, and he went on to forgive me and to come to Virginia Tech and to work together for more years than we like to think. So after the research center, the Systems Research Center was formed by the Navy at Virginia Tech. I began to work in projects that were of interest and funded by the Navy. Michael Overstreet, who's at the bottom on the left, and I worked on something called condition specification and the conical methodology. That was also part of our first Navy grant on model development environments, along with Osmond Balgi. Graphical analysis became a key part of the kind of thing we were doing, but it also was key to the work of this fellow on the right here, Lee Shrubin. Lee published a paper on event graphs that was very instrumental, very instructive to us as we were working on graphical analysis of process models and activity scan models. I show Mike's picture in the middle there because this, for those of you who know Mike, like Kara, that's where you see him more often on the other side of the camera. He's a very avid camera bug. Virginia Tech, we continued to do queuing analysis of dynamically reconfigurable networks. Although Narayan Bhatt and I were separated by quite a few miles, we continued to do that and have some, I thought we got some very interesting results for some very difficult problems. Began to work in software development methodology evaluation at a Navy request with a fellow named Sean Arthur, who's on the left. Sean and I have also published papers in the Winter Simulation Conference. And we began to look at the extension of the simulation, the conical methodology, condition specification, modeling concepts with a fellow named Ernie Page, who's on the right here. You know, Ernie is the sim guy, Sean is the slim guy, not. But there's a more familiar picture of Ernie in the middle there. I think he titled that one, "Three-Putting My Way Across Ireland." The objectives, principles, attributes framework developed with Arthur gave a basis for evaluation of software development methodologies. A very important, very timely contribution that we later put into our book, Managing Software Quality. The model development for parallel and distributed execution. That work was pushed by Ernie Page and, to a lesser extent, Mike Overstreet. That was the subject of Ernie's dissertation. And then there was the visual simulation environment, which shows what happens when two professors try to market something. And Osmond and I wrote very candidly about our failure. But it was a good failure. Relativistic time, simulation in real time. In other words, using simulation in conjunction with real-time experimentation that's ongoing. A fellow there, Srinidhi Varadarajan, he often went by just Srinidhi. Srinidhi has become a millionaire. He was the developer when we made the big splash at Virginia Tech about having an academic computer that was the fastest parallel computer in the world. That was Srinidhi. He was the power behind that. Events that have occurred: the History of Programming Languages 2 conference in 1993 in Cambridge, Mass. I did a paper on the history of discrete event simulation programming languages. And I consider another very important event that shaped my life and the invitation to co-author with Bob Sargent, the Perspectives on the Evolution of Simulation for the 50th anniversary of Operations Research. And then with Jim Wilson, you see here on the right at the bottom, Bob Sargent in a more familiar picture of Bob. We've been working on compiling a retrospective oral history of simulation, which is an NSF-funded project, and I invite you to attend our session on Wednesday morning at 8 a.m. To where we will give a status report on that project. The Navy influences were very important. I've gone through a number of these already. We intensified a program in 1973, an educational program with the Naval Surface Weapons Center, Dr. James E. Colvard and a fellow named Bill Duke. I served as an expert consultant in the summer and academic year, but of course I went on academic leave and spent 7 months there. And during that time, an interesting event happened that I think you will find a little remarkable. Dahlgren was doing the software development. A company on the West Coast was doing the hardware development for Trident. Trident is the third generation of submarine-launched ballistic missiles. They were doing the Trident simulation in SimScript. During their work developing the software on a simulation model of the hardware, they discovered 2 hardware errors. And that is, was very encouraging to me that you could get such a result that would left most people just saying, I'm not sure I believe it. We went to the SCSS was the Shipboard Combat System Simulator, and it was, if I had more time, I would discuss it in more detail. Now I'll dispose of a second myth, or at least clarify it. Grace Mary Hopper used to talk about where the term bug came from. She, in explaining it to me, actually to an audience, and I just happened to be a part of it, was that it came from discovery of a moth between the vacuum tubes on the ENIAC. Well, that's not really true. Her memory didn't quite live up to her at that time. It was actually in a moth discovered in a relay on the Mark II Advanced Sequence Control Calculator at NSWC, September 9th, 1947. The Mark machines came from Harvard, Howard Aiken. And when they sent the machine, you bought the machine, you bought a graduate student that came along with it. And that graduate student, a fellow named John Neiman, was still head of the computational analysis laboratory or department when I was at Dahlgren in 1979 and 80. 2 guys on the left here were very instrumental in bringing the center to Virginia Tech. Dr. James E. Colvard, the best technical manager I've ever met. Mr. James H. Mills, Jr., the most technically knowledgeable manager that I met. Jim Mills passed away a couple of years back. Jim Colvard still with us. Here's the picture to validate my claim. I don't know how well you can read it from that far, but what it is a picture they took of the moth that was in relay number 70, panel F, that was found that was causing the error. And it says, first actual case of bug being found. Okay? Just had to share that with you. Concluding summary. Your career is not so much about you as it is about others. And I cite my wife for giving me this quote, I am a part of all that I have met. That comes from Alfred Lord Tennyson. I think the impact and future of simulation is best measured by the fact that of the languages in History of Programming Languages 2, 4 of them cited Simulus 67, 4 of the 8, as the source of their fundamental principles. Now that's quite an impact. I also will use the same quote that Bob and I concluded our 2002 paper with in Operations Research. I'm going to enlarge it here so that you can see it better. And this is J.C.R. Licklider, who in 1967 was the director of Project MAC, Multi-Access Computing. And he says, and I will read just in case you're too far back, in their dynamic form, however, computer program models appeal to the recipient's understanding through his perception of dynamic behavior. That mode of appeal is beyond the reach of ordinary documents. When we learn how to take good advantage of it may, indeed, I believe it will, be the greatest boon to scientific and technical communication and to the teaching and learning of science and technology since the invention of writing on a flat surface. I thank you for your attention, and I conclude at this point. Sorry I read a little late.
Dick, on behalf of WSC Board, the WSC Planning Committee, and all of our members here, I want to thank you for the wonderful Titan Talk.
Thank you
and for
very
all
much.
your years of service, sir.
Thank you. Thank you.
Thank you, sir. And Dick will be available for questions if anybody has some other questions. Thank
Yeah,
you.
Or at the reception tonight, if you want to corner me there, feel free. I'm buying?
I wasn't going to cut you off.